This is our final project report for EE4430. My name is Scott Kauzlaric.
I'm Jacob McDonald.
And I'm Gary Robinson. We're going to describe the DC to DC boost converter that we designed and constructed, talk about its performance and how well it met the goals of the project.
Alright, first we're going to talk about the specifications or objectives of this DC boost converter. The main idea was to take a 9-volt DC input and produce a 12-volt DC output with a ripple voltage of less than 2% and to have it produce or to be able to drive a load of 4.5 watts or less. And the efficiency goal was to have it greater than 60%. Later we will describe the actual output of the DC converter. What we wanted to add to this was an input protection for both over voltage and over current. And the other thing we decided to add was a closed loop control to handle a input voltage ranging between 8 and 10 volts. And the idea was we fluctuate the input down to 8 volts, we'd still have a 12 volt output, and up to 10 volt input, we'd still have a 12 volt output.
And we'll quickly go through how we came up with our component values. First of all, we wanted to operate in the continuous mode, so we had to use this set of equations. We chose an operating frequency, or a switching frequency of 30 kilohertz. We knew our voltage, we knew our approximate power that we wanted out of it, so we could find our load resistance. Duty cycle was found with the formulas given in the textbook and in class. The same with the minimum inductance and minimum capacitance, and we actually went with a 470 microhenry inductor and a 220 microfarad capacitor.
To start with, I'm going to explain a little bit about the circuit, how we constructed the board, and what the various sections of the circuit do. Okay. Behind me is the schematic for the board. To start with, most of the DC to DC converter is a basic textbook circuit, and let's face it, it's not that difficult of a core circuit to design and construct. We did add a front end section both that has an indicator for power with a simple LED and an SCR circuit that functions as both over voltage and over current protection. There's a direct fuse in the power line that will blow if the circuit draws too much current. That's the over current protection section. The SCR and an associated Zener diode and resistor function as over voltage protection. If the input voltage exceeds the voltage of the Zener diode, that will begin to conduct. It will cause a gate voltage to appear on the SCR, and the SCR will conduct. It's connected directly across the power line and the ground line, so when the SCR conducts, it will pull current through the fuse and blow the fuse. This is known as, it's a fairly standard thing known as a crowbar circuit, just like throwing a crowbar across a pair of electrical wires. After that, we get into the core of the converter, where we have the inductor, the switching device, the MOSFET, a diode, and an output capacitor. Now the inductor we oversized to ensure that we're running in a continuous operation mode. The capacitor is also larger than the minimum capacitance so that we could keep the ripple down below the specification that we were given. The MOSFET is driven by a MOSFET driver, the same one that's been used in the lab in the course, in order to ensure that we're positively switching on and positively switching off in order to keep any switching losses to a minimum. After that, the extra part of the circuit too, of course, is that we need a PWM source in order to drive the MOSFET. That's this device down here, a linear technology chip, which will produce a PWM signal where the duty cycle can be controlled by an input of 0 to 1 volt input signal. That functions as a feedback from the output. It's resistor scaled so that at our desired output, we're producing our desired PWM. It's a feedback mechanism. And a simple voltage regulator to produce 5 volts simply in order to power the PWM controller chip. Once we had the circuit more or less designed, it was simulated in PSpice in order to verify that the performance would be roughly where we would want it to be. At least the boost converter section was simulated. After that, we picked out component values, ordered them, and laid out a small circuit board to solder everything onto. We wanted to have a robust circuit, so it made sense to put it on a little circuit board. We actually designed and laid out a small circuit board. Not only is it much more robust than doing something with either a plug-in breadboard or wire wrap or a perf board method of construction, this type of thing also allows modifications to be made fairly easily to the circuit, and in case something were to go wrong, it's fairly easy to repair too.
I'm going to demonstrate the steady state operation of the boost converter. On the input we have 9 volts. The output we have 12 volts. Okay, and this is our output voltage ripple. It is peak to peak around 196 millivolts, which gives us a ripple rate of approximately 1.7%. Okay, and now we're going to demonstrate our feedback loop, how the output voltage controls the duty cycle. We've got our channel 1 connected to the input of the MOSFET driver, and channel 2 is our output voltage. Now what we want to happen is when the output voltage goes down, this pulse width should increase to compensate for that. The input voltage, excuse me. And we're going to drop the input voltage down to 8 volts, and the pulse width does increase to try and compensate for that. And it keeps going as the input voltage goes down. And the opposite thing happens as the output voltage goes above 9 volts. The pulse width decreases. Okay. Now I'm going to demonstrate our input protection circuit. If the input voltage gets to right around the Zener voltage of our Zener diode on the input, the fuse will blow and the output will drop to 0. And right about 12 volts it was.
Okay, I'd like to spend just a short time to show you the actual circuit, the board that we built, and kind of give a little explanation of what's on it and what it's doing. As I'd mentioned, we actually made this on a circuit board, both for reliability and repairability. The components were all purchased from DigiKey, a fairly standard industrial and commercial source. The circuit board comes from Express PCB. They do a nice job over the internet of fabricating small quantity, low-cost prototype boards. What we have on here are input and output connectors, a fuse as part of our input, the SCR, that's part of the overvoltage protection circuit, then the MOSFET, inductor and Schottky diode that form the core of the DC to DC converter. An output filter capacitor, and the output is fed back through an adjustable potentiometer to the PWM control circuit, control chip, which then generates the PWM signal as an input to the MOSFET driver, and the MOSFET driver, of course, sends an output to the gate of the MOSFET to drive the entire boost converter. The two resistors out here are our 32 ohm load. It's two series connected 16 ohm resistors. There are also 50 watt resistors, because although this device only produces 5 watts approximately, 4.5 watts, you'll be surprised how warm those get after running for a minute or two. The resistors are oversized. The inductor is actually oversized, both in terms of inductance and the actual DC current handling capability. Same for the Schottky diode. Everything on here has a safety factor of at least 2 or 3x from what the minimum design requirement is.
Next, we're going to cover the results of our DC converter based on the demonstration that you just saw. As we discussed earlier, here are the specifications that we were required to meet for this project. And the results, due to our tuning ability on our board, we were able to tune it to an output right at 12.0 volts. The ripple rate was 1.7%, which could have been reduced if we did more filtering, but it, with what we had, worked well. Our output power ended up being exactly 4.47 watts. The measurement of our output resistance was 32.2 ohms, which lowered our output power just a little bit, giving us a resulting efficiency of 90.9%. If you noticed in our demonstration, the output voltage when tuning the input, when we changed it down to 8 volts, you probably saw that the output did sag, and when we increased it also, the output did rise. And that was due to the duty cycle changing, but not changing enough. And we will explain that more later in our summary.
Okay, and that was our DC converter. Overall, we're pretty happy with the results. We met all the specifications. What we really wanted to happen was, what we really could have improved was the feedback loop to have some more dynamic control. And we think we could have done this by adding an amplifier in the feedback loop, because what we were getting was a change in duty cycle, but we needed basically double the change in duty cycle as we were getting, so maybe we could incorporate some kind of doubling amplifier in there, and we think that would have solved our problem, and we could have gotten a 12 volts out or 8 to 10 volts in. And the cost of our project for the board was kind of pricey. The components were around $22. We could have reduced that a little bit, but beyond those few things, we're pretty happy with the results.